Okay, so welcome back. So before, in the previous video, what we did is we showed that I can basically, by letting big N get I can find you a big N, which is an element of the natural numbers, such that the partial sum gets arbitrarily close to the infinite series, i.e. what the infinite series is converging on, which we called mx. Okay, so if I just replace mx with this infinite sum, so I get that the infinite sum, I is equal to 1 to infinity, of the modulus of xi to the power of p minus the sum from I is equal to 1 to big N of modulus of xi to the power of p is less than epsilon, where epsilon is any real number I like. So I can make this arbitrarily small, okay? So basically, if I just rewrite this, this is the sum from I is equal to n plus 1 to infinity of the modulus of xi to the power of p, and I can make that arbitrarily small is what this is telling me. So the fact that this infinite series is converging to mx means that I can find you a point where the tail end of the series, has to be arbitrarily small. If you sum up the tail end of the series, it's arbitrarily small is what this is saying. Okay, so I'm going to let arbitrarily small actually equal epsilon to the power of p over 2, and you'll see why I'm doing that. Basically, I'm letting the epsilon here that's in here now, and it's rather confusing notation, I admit. This epsilon was just a placeholder, basically. I was just using epsilon because it's conventional to use epsilon. I was just using epsilon here to mean something that I can make arbitrarily small. Whereas now, this epsilon I'm using here is the epsilon I'm referring to up here, which is this epsilon I'm taking my sequence x, which is this sequence in LP, and I want to prove that there is a point in S which is a distance less than epsilon away from x. So I'm letting this epsilon in here, this epsilon to the power of p over 2, be the same epsilon as up there, basically. So I'm saying, basically, that you give me an epsilon, and you've challenged me to find a point of S within this ball around x of radius epsilon. What I'm saying is I can find you some big N, which is an element of the natural number. There exists a big N, which is an element of the natural numbers, such that the sum from I is equal to n plus 1 to infinity of the modulus of xi to the p is less than epsilon over p to the power of p over 2. So you've given me a sequence, and I'm saying, okay, I'll take your sequence and I will find you a big N, which is an element of the natural numbers, such that the tail end of your sequence turned into this series is less than epsilon to the power of p over 2. I can do that. You can't stop me doing that. It might be a bit of an odd thing to do, but you can't stop me doing that. And the reason this is interesting is because if I consider now the set T big N, so this big N is the same big N here that I found, which was specific to the sequence X. Okay, so if I consider the set big Tn, which we know is a subset of S, well, set big Tn was the set of all sequences Q1, Q2, Q3, all the way up to Q big N, and then it had 0 after that term, the nth term, all zeros after that, but the first n terms, Q1, Q2, all the way up to Qn, big N, can take on any numbers in the rational numbers, so they can take on any rational value. So this was a set of sequences, basically. Okay, so I'm just going to move this up a bit. Right, so what I'm going to do now is I'm going to show you that I can find you a sequence, specifically this sequence you wanted me to find in this sequence you wanted me to find in S, which is epsilon close to the sequence X. It's going to be in this set here, okay? Right. So, I have my sequence X here, which is X1, X2, X3, all the way up to Xn. No, it doesn't go all the way up to Xn, it goes on. Well, it does have an X big N term, but it goes on. It's infinitely many terms, and these are all, we're assuming, real numbers. The only constraint on this, remember, is that the sum from I is equal to 1 to infinity of the modulus of xi to the p is finite. Okay, so if I want to now calculate the distance between x and, let's say, some sequence t, which is an element of this set Tn. So let's say T is an element of this set. What's it going to equal? Well, it's going to be the sum from I is equal to 1 to infinity. Just by the definition of the metric on our LP space, this is going to be the distance x between t is going to be the modulus of xi minus ti to the power of p, all to the power of 1 over p. So whatever Tn and S are, they are subsets of L infinity, so we're using the metric on L infinity now. Okay, and these sequences are both elements of L infinity. Okay, this is equal to, because Ti gets to, after n, if you look at the n plus 1th term and the n plus 2th term, all the terms after n are just equal to 0. So we could split this up into two parts. We could say that this is the sum from I is equal to 1, firstly up to big N, and in that part you need xi minus ti to the power of p. But then after that, if we sum it up from I is equal to n plus 1 to infinity, after that, for all of the n plus 1 terms, this is all equal to 0, so this just becomes the modulus of xi to the p, and then obviously we're going to have to take the whole thing to the power of 1 over p. So all I've done is split this infinite series into two parts, a finite part and this infinite part, and that is why me being able to bound to the tail end of this sequence is going to turn out to be so important later. And also, you might even see why I've chosen the specific combination epsilon to the power of p over 2. Okay, so now, this bit here, so we've got a nice bounding on this, it's up here. This bit here is a bit more of a problem, but it's not a problem because xi is a sequence of real numbers, remember. So we have these x1, x2, we're now just interested in up to the x to the n term. And in the t sequence, so this is the sequence x, this is the first n terms of the sequence x. I don't care about the sequence the terms after that. And then we'll put the first n terms of the t sequence as well. Well, the t sequence can take on whatever rational numbers you want, q1, q2, qn, and it will still be an element of Tn. I didn't say specifically what t sequence I was using yet, so I can let it be whichever sequence in here I like, and this fact here, this splitting of the sum into these two parts will still work. Okay, so I can make these rational numbers arbitrarily close to the real numbers is the point here. I can make xi minus ti, as arbitrarily small as I like. So I can make this modulus as arbitrarily small as I like, and then I can raise that to the power of p and it's still as arbitrarily small as I like. So I want you to make this sum less than epsilon to the p over 2. So what I want to do is make the sum I is equal to 1 to n of the modulus of xi minus ti to the power of p, and I just want to emphasize q1 is t1, q2 is t2, qn is tn, etc. I want to be able to make this less than epsilon to the p over 2, and the reason you can do this is a finite sum, so this is modulus of x1 minus t1 to the p, plus all the way up to modulus of x big N minus t big N to the power of p. Because you can make rational numbers as close as you like to real numbers, I can make each of these modulus bits as small as I like. So for instance, I can make each of these little bits here, so let me get my colour pens out. Where's the blue pen? So I can make each of these little bits here smaller than, let's say, epsilon to the p over, how many of them have you got? Let's say 2 to the n. I'm trying to make the whole sum less than epsilon over p to the 2n. So if I make each of the components, so each of these individual bits here, so let me get the blue pen back again, each of these bits less than epsilon over p to the p over 2 to the 2n. So I divide this, sorry, I want to make that less than epsilon to the p over 2. So if I make each of the n bits that you're adding up to get the thing that you want to be less than or epsilon to the p over 2, and I make them less than epsilon over p to the over 2 to the n, 2 times n, I'm sorry, it's a bit of a word twister. That will meet my conditions. So what I now then just need to do is I need to make x1 minus t1 less than well, I won't put that, the epsilon over p, epsilon to the p over 2 times n to the power of 1 over p, if I make x1 minus t1 less than that, and I do that for all of them, so I make xn modulus of xn minus tn less than epsilon to the power of p over 2 times n to the power of 1 over p. Got it. If I do that for absolutely each of these terms that we're adding up, then it will work, basically, that all of them summed together will be less than epsilon over to the power of p over 2. And the reason you can do this is because, as I say, you can get rational numbers as arbitrarily close as you like to real numbers. That's just the statement that rational numbers are dense within the real numbers. So we're using the fact that the rational numbers are dense within the real numbers. So I can make this sum here, so this component here, less than epsilon to the power of p over 2, which means that, let me turn over. So, we'd said that the distance between the sequence x and this sequence t was going to equal, well, by definition it was going to be equal to the sum from I is equal to 1 to infinity of the modulus of xi minus ti to the power of p, all of that to the power of 1 over p, which we had split into two parts. The sum from I is equal to 1 to n of the modulus of xi minus ti to the power of p, but because the sequence t was an element of big Tn, i.e. after the nth term all of the terms were 0, then the second part just becomes the modulus of xi to the power of p, and that's because the ti's are all 0, so you could subtract 0 from all of those, but it's kind of pointless. Okay, and we'd already bounded this tail end of the sequence. We chose big N so that this tail end of the sequence was less than epsilon to the power of p over 2. I've now said that because the ti can vary over all rational numbers, we can make this less than epsilon to the power of p over 2. So this overall is going to be less than or equal, strictly less than epsilon to the power of p over 2 plus epsilon to the power of p over 2 to the power of 1 over p. So, add those two things together, we get epsilon to the p, do it to the power of 1 over p, we get that this is equal to epsilon. So I've made the distance between x and t less than epsilon. So basically, what I've done is I've shown you that you give me any epsilon, I can find you a sequence t, which is an element of t big N, such that it is arbitrarily close to epsilon. And the way you decide that big N is you find a big N that will make a big N such that the tail end of the sequence, the sum from I is equal to n plus 1 to infinity of the modulus of xi to the p is less than epsilon over to the power of p over 2. That's the way you find that big N. Okay, so that's how you prove it. That's how you prove that this set S is dense within the L infinity space, because what we've done is I've shown you that you give me any point, any sequence in the L infinity space, I will find you some sequence in the set S, which remember contains all sequences in the Tn's, so it's the countable union of all the Tn's. So whatever big N you get, it will correspond to one of the Tn's in this set S. So the sequence will be in S. So basically, that's the proof that this set S is dense. So S is dense in L infinity, in LP rather, in LP. Okay. And since S is also countable, that implies that the LP is separable. So LP is separable. Okay, so now I'll just discuss briefly the alterations you have to make if LP is complex LP space. Okay, so the first alterations you have to make is that you have to make the sets Tn's, you have to make them sets of sequences, and instead of rational entries for the first n terms, you have to have Gaussian numbers there. So let's say, let's still call them Q1, Q2, all the way up to Q little n, and then zeros afterwards. But now these Qi's are elements of the Gaussian numbers. Now the Gaussian numbers is still a countable set. It can be put in bijection with the rational numbers across the rational numbers, so Cartesian product. So because the rational numbers are countable, it implies the Gaussian numbers are countable. And for the same argument as why the Tn's are countable in the rational case holds for this case, because this is effectively the Cartesian product, the n Cartesian products of the Gaussian numbers. So it's effectively got the same cardinality as the set, which is n Cartesian products of n lots of the Gaussian integers. And if you Cartesian product finitely many countable sets with one another, you also will get a countable set, basically. So that is going to be, the Tn's are going to be countable sets. Then what we define S to be, it's exactly the same. We define it to be the countable union of all the Tn's. And then what we want to prove, that's also countable, again for the same reason that countable union of countable sets is countable. And then what we want to prove is that this set S is dense within the L infinity space. So what you would do is you take an arbitrary element x, which is in L infinity, so that's just some sequence x, which is x1, x2, etc. Okay, and then you'd say, okay, find me. So you give me an epsilon, and you challenge me to epsilon greater than 0, and you challenge me to find a sequence in this set big S, which is a distance from this this sequence less than epsilon. Okay, so I say, okay, if you want me to do this, I will find you a point in this big N where the sum from I is equal to m plus 1 to infinity of the modulus of xi to the power of p is less than epsilon to the power of p over 2. So okay, once you've given me the epsilon, what I do is I find you a big N, which is an element of the natural numbers, such that after that big N, the tail end of this series sums up to less than epsilon to the power of p over 2. Then, if I take the distance between x and an element t, where t is now an element of t big N, so it's some sequence of Gaussian numbers up to the big nth term, then this is going to be equal to the sum I is equal to 1 to infinity of the modulus of xi to the power of p all to the power of 1 over, minus ti to the power of p all to the power of 1 over p. I'm sorry about that mess in the middle there. So that's correct. And then what we do again is we split this up into two parts. We say that this is the sum from I is equal to 1 to big N of xi minus ti to the power of p, plus the sum from I is equal to big N plus 1 to infinity the modulus of xi minus ti to the power of p, all of that to the power of 1 over p. And basically we've now said this is bounded by epsilon over p to the power of p over 2, and exactly the same argument as in the real case holds here. I can find you Gaussian numbers. This sequence t is some sequence q1, q2 all the way up to q big N, and then 0, 0, 0, 0 afterwards. But these can take on any Gaussian numbers, and I can basically get these as close to these complex numbers as you want, and make these moduli as small as you want, and then do that to the power of p, and it's still as small as you want, and then do a finite sum, and it's still as small as you want, can get it as small as you want. So make it smaller than epsilon to the power of p over 2 by picking these Gaussian numbers cleverly. So these qi's are all elements of the Gaussian numbers. Okay, so that then implies that this distance is overall going to be less than epsilon. So I've done what you asked me to do. I've found you a sequence such that the distance between any point, any arbitrary point in the LP space, and basically I found you a sequence. Basically, you give me any sequence x, which is an element of your LP space, and I will find your sequence in this set big S, which is arbitrarily close to, I can get, you get arbitrarily close to your point x, and I can always find you some element of this set which is within that distance of your point x. So indeed, S is again dense within LP. Why have I put L infinity there? That should be LP. I really apologise if I have been putting L infinity where I'm saying L infinity when I mean LP. It's a member of LP, not L infinity. So yes, LP, whether it's a real or complex metric space, is a separable metric space.